To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. The capacitor is a charge storage device. The most basic behavior is the charging and discharging. However, it is not worthwhile in this lab to have a separate task and a circuit just to demonstrate this simple and basic behavior, as there are 3 other circuits in which this property is applied in more meaningful contexts. Hence, it is sufficient for step A1 to observe a few demonstrations, and write a short report of your learning and understanding. No hands-on work is required. You might have seen these classics. Now just sit back, relax, enjoy this current step A1 feature. One important feature is how the rate of charge and discharge can be controlled with resistance. We say resistance, not resistor, because resistor is not the only device that has resistance to a current. Virtually all devices, except for superconductors, such as inductors, LEDs, transistors, solid-state chips, even wires have current resistance. The key concept is that the higher the resistance of the path connected to a capacitor is, the lower the rate of charge and discharge will be. We will start by studying a simple circuit shown here, which is used in a series of demonstrations of the step A1 in the follow. You are not required to build this circuit. However, you should gain an understanding of what the circuit does to demonstrate the capacitor charge and discharge behavior. The main element is the 470 microfarad capacitor, which you should have at least one. One terminal is connected to a 25-volt DC source. The other is a manually movable connector that can be switched to different positions on the circuit to charge or discharge the capacitor. In order to visualize the charging and discharging processes, one bank of 3 serial by 4 parallel LEDs is inserted in the current flow path for discharging, and another similar bank of LEDs is used in the path of charging. A number of resistors are also placed in the charge and discharge path in series with the LED banks. These resistors are selectable by moving the capacitor switchable terminal to their contact positions on the circuit board. The resistors allow control of the rate of electrical charge flow, that is, the current. This is similar to what we did in Lab 1. Most relevant for your work of this step A1 is the setup for measurements that you should take note in order to describe, explain, and discuss for your report of A1. There are 2 quantities. The voltage across the capacitor as a function of time, which is measured by the DG length AD2 scope 1. And the current that is indirectly measured via Ohm's law as the voltage across a 1 kilo ohm resistor, measured with scope channel 2. Various aspects of the circuit will be clearer in the series of demonstrations in that follow. If you are already familiar with resistor-capacitor circuits, this part will be trivial. For the simplicity of a pure RC circuit, the LED block in the circuit can be bypassed. The idea here is that by choosing different resistances, the charging current when the switch is connected can be controlled and its time-dependent behavior can be studied. In Lab 2, the capacitor is compared to a water storage tank. Here, the same analogy is used. In filling a water tank, which of the 3 inlets with different orifice sizes will allow the filling be the fastest, and which one, the slowest? Imagine you are doing this experiment. In each step in the follow, the capacitor will be first shorted to drain all of its charges. Then it will be charged through the choice of different resistors. The scope trace will display the capacitor voltage as a function of time. See if you have an intuitive understanding of the time-dependent behavior. The first resistor is 1.5 kilo ohm. The second resistor is 1 kilo ohm. The third resistor is 470 ohm. A quantitative comparison shows that for 1.5 kilo ohm resistance, the scope trace indicates that it takes about 1.9 seconds for the voltage to reach 90% of its 25 volt maximum. For 1 kilo ohm, it takes a shorter time, approximately 1.2 seconds or so to reach 90%. Observe one more time 1.5 kilo ohm versus 470 ohm. For the 470 ohm, it takes approximately just half a second to reach the 90% voltage level. Although these estimates of the charging times are approximate and not of high precision, the trend is unmistakable. The lower the resistance is, the more rapid the charging will be. Observe, form your own interpretation. Feel free to apply what you have learned from other courses or elsewhere about RC time, then write your report. Capacitor is an energy storage device. Charging, or building up energy, is not the same as discharging, which can be dangerous. The following discharging experiment is much less dramatic. Instead of an exploding iron wire, the visualization is achieved with 12 LEDs, whose brightness will be the indicator of the discharging power. Again, in parallel the water tank analogy, which outlet of the three will release water with the highest flow rate. We use three resistances, 1 kilo ohm, 11 kilo ohm, and 34 kilo ohm. The question here is not only which resistance allows the highest discharge current, but also how long is the discharge. Observe the relationship between the brightness of the LEDs versus how long the LEDs stay unlighted. This shows the correlation between the schematic and the breadboard circuit. Shown are the LEDs and the set of resistors. Keep in mind that one resistor, the 1 kilo ohm, will be used to measure the current via Ohm's law, using scope channel 2. Observe the 12 LEDs in the following. First, discharging through 34 kilo ohm resistance. Observe the brightness and duration of the LEDs. The recording camera, which has an internal auto gain that adjusts the image brightness, does not represent the gradual decline of LED brightness as well as with the human bare eye. Next, discharging through 11 kilo ohm resistance. The initial LED brightness is noticeably higher than the previous. The voltage, yellow, top left, and current, blue, bottom left, also show faster decline. Lastly, discharging through 1 kilo-ohm resistance. The LED were so bright that they saturated the camera, and the current scope trace on the left was off scale. But the LEDs also dim much more rapidly. The relationship between LED initial brightness and the duration of lighting is straightforward. It is a trade-off due to the constraint of the total energy. The energy each discharge is the same. Hence, if the energy is fast released, with high LED initial brightness, then the lighting is short-lived. And vice versa. This accelerated video shows the measurements of the voltage and current for the 3 cases. From the data, the total energy is obtained as the given formula. And the results indeed show the net energy released is approximately the same for the 3 cases, explaining the trade-off between initial brightness and the duration of the lighting. In addition, as it should be, the energy absorbed by the circuit is approximately equal to the lost storage energy of the capacitor. Note that voltage is not the initial full V source voltage across the capacitor, but is subtracted by the contact potential of the serial LEDs, because at this voltage, the LED current is 0 and the capacitor stops discharging. If discharging current can power the LEDs, so can the charging current. Is there any similarity between charging and discharging? Let's do an experiment to find out. In this demonstration, the 2 banks of LEDs are practically equivalent, both have the same series resistance and practically the same electrical properties. The switchable terminal of the capacitor is alternately moved to connect to each bank of charging and discharging LEDs. Observe and compare. Do charging and discharging have similar behavior? Both processes, charging and discharging, exhibit the symmetric behavior, an initial high brightness flash, then followed with an approximately exponential decrease in light output. This will be repeated. Observe the time. Do both take a similar amount of time? Note that the LEDs remain lighted for a reasonably long time because of the large capacitance. What do you think if the capacitance is not so large? Remember Lab 2, Part A, when we compared the 470 microfarad versus 10 microfarad. Here we will do the same thing. Observe the experiment repeated with 10 microfarad. What can be concluded about the effect of the size of capacitor on the time behavior? If this graphics represents your observation and intuitive understanding from the demonstration about the symmetric charging and discharging behavior, as well as the effect of capacitor size on the time behavior, you have achieved the objective on learning about this capacitance effect. This is the end of Part A, Step 1. This step aims to illustrate the basic capacitor charging and discharging behavior. What is the most fundamental notion in all the demonstrations above? It is the same as what we learn in Lab 4 Part 1. The notion of time. Virtually all physical cause and effect processes involve time, and nothing can be instantaneous. The charging and discharging of a capacitor involves the flow of charges, and how fast the process is, depends on the charge flow rate. We have used the water flow analogy quite a bit. This time, let's use a different analogy. Given a population that want to go from location A to location B, say, evacuation before a hurricane. What happens if the large multi-lane highway on the left is rerouted to a single-lane traffic on the right? A normal 1-hour trip might become an 8-hour trap. Instead of tens of thousands of people evacuated within 1 or 2 hours, it may take 10 or more hours. The resistance is like the inverse of the size of the highway. Low resistance allows high charge flow rate and the capacitor can be filled up or drained fast. But how long it takes for a capacitor to be fully charged or discharged also depends on its size. Given a finite flow rate, the larger the capacitance, the longer it takes to fill up or drain out. Hence, both R and C have effects on the time behavior, and you might have learned the RC time constant from circuit theory. Here, the characteristic RC time behavior is demonstrated for an intuitive, visually direct learning experience with the LEDs, whose light intensity represents the current, and the lighting duration gives a gut feeling of the RC time. This is the reason the 470 microfarad capacitor was used, so that the time scale is in the range of human visual experience. Smaller capacitor would result in too short a time for us to observe. No LEDs were harmed during the filming of these videos. The study in previous step A1 on the capacitor charge and discharge behavior was conducted manually. The circuit to be built in this step A2 is a further study of the charging, discharging, and even reverse charging, that is, charging to an opposite polarity behavior, and all done automatically by the circuit itself, without any need for external input control. The circuit can also be considered as a further study of the OpAmp property, in which the ultra-high gain in open-loop configuration causes saturation and instability. This creates a non-stationary condition, that is, the circuit cannot settle to any stationary state with constant voltages and currents. Instead, it keeps on vacillating between the states. Vacillation, or oscillation, entails the concept of frequency. The top graph shows how the OpAmp cannot stay still, because the output feedback tries to stabilize, or make the two inputs roughly equal, to no avail, because the moment the inverting input, VA, catches up with the non-inverting input VB, it takes only a small overshoot or random noise to make the output flips the non-inverting input VB the other way, and the inverting input VA starts the chase again in the opposite direction. How fast it vacillates back and forth depends on the time it takes to fill the capacitor to the level of the non-inverting input. The bottom graph shows how the oscillation frequency can be varied by changing the required fill level of the capacitor. Alternatively, the feedback resistor can also be varied to control the frequency. However, the circuit is sufficiently complex with one potentiometer. Rather than using two potentiometers, the feedback resistor can be changed manually. Here, once again, there is a link between the characteristic response time versus the frequency, like what we learned in Lab 4 Part A. The shorter the characteristic response time, the faster the circuit oscillates, analogously to the impulse response time versus the frequency bandwidth that we learn in Lab 4. In circuit theory, you see that the RC characteristic time is a key parameter of the circuit frequency response behavior, and for the linear Laplace transformed circuit, each RC time is a root or pole in the circuit frequency response function that defines the circuit behavior. Don't worry if you have not learned Laplace transformed circuit yet. It is sufficient here to realize that RC time is not just about the current exponential behavior in the charging and discharging as seen in previous A1 demonstrations, but is also related to the oscillation frequency of a circuit. Hence, this OpAmp self-oscillatory circuit is intended to further reinforce your intuitive understanding, or quote-unquote gut feeling about the connection between the RC response time to frequency. It is also a prelude to the concept of using RC time in frequency filters later and in Lab 6. Also, rather than thinking about frequency in abstract, the circuit is used to show that RC time control can generate phenomena in two ranges of frequency with direct human audio and visual experience, seeing LEDs blinking, and hearing sound output. It is hoped that the direct audio-visual sensory experience will help you develop an associative memory and intuitive learning on the topic of RC time and frequency in Laplace transformed circuit theory. The wiring diagram from the wiring help app of the circuit can be a bit too compact for photography, as the components are placed close together. Especially the parts for light and sound are too close side by side. This is not necessary. The photograph of an actual circuit shows a more spread out circuit. This circuit is built for photographic clarity. The R and C combo for sound is placed far away from the OpAmp, leaving room for the RC combo for LEDs, and also room for the wires that lead to two large rows of LEDs, which are used to test the circuit numerical simulation. If your breadboard real estate is not an issue, it is recommended to build a circuit with generous space between the components for the ease of troubleshooting as well as for presentation. Connect two jumper wires to the configuration for sound only, no LEDs. Then connect the AD2 scope channels to positions as indicated. If you have a buzzer, it is optional, but the AD2 can generate sounds via your computer speakers. You can use your smartphone spectral analyzer app to measure its frequency. Do not be concerned if the AD2 sound does not sound correct, the audio effect is only for the human sensory experience. Use the built-in scope frequency measurement to determine the frequency of your output as a function of the potentiometer tuning. Remember, there is no input, the circuit oscillates by itself and do not connect any waveguide channel to anywhere on the circuit. The nominal values for R, 15 kilo-ohm and C, 0.1 microfarad in the circuit design give 1.5 millisecond time constant. The recommended frequency range for your experiments is from around few hundred Hz to a few kilohertz. Feel free to adjust the values to your preference. The work is quite straightforward as explained in the instruction here. Besides the demonstration of varying the frequency, the only measurement is to verify the relationship of characteristic RC time tau, frequency f, and ratio eta between Vmax and V saturation, which can be read off the scope traces. Connect jumper wires to the configuration for LEDs. Then connect the AD2 scope channels to positions as indicated. Since the human eye is not sensitive to light brightness modulation higher than 20 or 30 Hz, and the LED can be bright, with a strong visual after effect, the RC combo should be such that the frequency is in the range of few Hz at best. In order to supply sufficient current to light up many LEDs, it is also necessary to have high capacitance, hence, at least 100 microfarad is recommended. Wide space between components can help the ease of putting in and taking out jumper wires, when switching between sound generator and LED blinker. A pair of fine tip pliers can be useful. Good visual acuity would have helped the recognition that one wire end was bent sideways, and should have been straightened. After a mighty struggle, the jumper wire is secured in its location. When using LEDs in parallel, they all should be of the same type. Here they are not, but the group of low band gap, that is orange and reddish, are grouped together, and the high band gap type, green, blue, and white are grouped together. At high frequency, the camera, which is 25 frames per second, can no longer accurately represent the blinking behavior, which is why in a later video, the photoreceiver of Lab 4 was used to measure the LED light output behavior. Once the circuit appeared to work as expected, measurement or monitor should be set up for data collection. The LED's emissions are more complex than what the camera and the scope trace can show. The yellow scope trace only shows the voltage across the capacitor. The LEDs actually have a short drop-off after the initial flash, and the two types, the reddish and the bluish, have different behaviors as well. This can only be measured with a photoreceiver as shown in another video. The task stipulates the measurements for 3 LED blinking frequencies. It will take time to measure the blink rate below 1 Hz. Be sure to take appropriate data for the frequency analysis discussed above. There is one potential pitfall in measuring the frequency, as discussed a little later. Beware of a possible small hysteresis effect, that is, the blinking frequency when sweeping up might be slightly different when sweeping down, when the potentiometer is set at the highest capacitor voltage. Best is to always sweep in one direction when collecting the frequency data. If the frequency is being chirped, the frequency measurement by AD2 scope is not accurate. Hence, allow sufficient time for the frequency measurement to settle before taking data. Observe that even with a small tuning change, it took seconds for the frequency values to gradually and asymptotically approach to its constant values. In Lab 2, we use a signal generator to drive the rectifier circuit. The oscillator circuit here can also be used for that purpose, as illustrated in this video. This video is to illustrate the synergy between the lab assignments. The photo receiver of Lab 4 is used to study the OpAmp LED oscillator of Lab 5. The purpose is more than just a simple study the LED behavior, but an encouragement of the beginner experimentalist student to play, tinker with the circuits one created, and it provides a rudimentary guidance to common mundane experimental practices and pitfalls, which a beginner usually have to go through to move up on the learning curve. The previous videos represent mainly the study of frequency, not the current and the LED output. The camera is a limited instrument, because of its low frame rate as well as of its complex auto gain and adjustment that distorts the optical signals. This video is a more accurate study of the current and LED behavior on a speed much faster than the human eye by using of the photo detector developed in Lab 4. In principle, all parallel LEDs should be of the same type. Here they are not, however, they were grouped together according to the band gap, or contact potential. Low band gap materials, yellow, orange, reddish, were parallel in one row, and the high band gap type, green, blue were in another row. The oscillator was allowed to run at higher frequency than previously. The LEDs predominantly emitted light in the vertical direction. The photodiode also faced up, which detected light from the ambience. Hence a cover can enhance the coupling between the LED and the photodiode as well as blocking ambient light for a more accurate measurement. The scope trace data can be compared with the simulation model. Because of the large difference between contact potentials, the high band gap blue-green group had a longer duty cycle within one period than did the yellow-red group. The simulation accounts for this overall qualitative features. An observation here is that the blue-green LEDs are more efficient light emitters than the yellow-orange-red LEDs. This is actually a well-known properties of these LEDs. As evidenced by the yellow scope trace, which is proportional to the LED current, both LED rows had comparable current, yet, the optical signal of the blue-green LEDs was much higher than that of the yellow-orange-red ones. A similar series of demonstrations showed a wide range of the oscillatory LED voltage and current behaviors under different experimental conditions, that are consistent with the model simulation. In summary, this circuit is simple, but can provide many useful learning subjects about the capacitor and the RC circuits. It takes time for these calculations, from tens of seconds to minutes. These are calculated LED current and voltage as functions of time. This shows the voltages of the three OpAmp terminals: output node C, red, inverting input node A, green, and non-inverting input node B, yellow. Notice the frequency with the LEDs is lower than that without. These are default values. They should be changed to the actual values on the circuit. For each change, the circuit is recalculated. Note the difference frequency, different LED voltages and currents, compared with the previous results. These types of behaviors are shown in a demonstration video, in which a photodetector was used to measure the LED outputs. Select the correct LEDs. The calculation uses somewhat old LED calibration, but it can still give some reasonable approximation, and generally qualitatively valid LED behaviors. Notice again a different frequency. Quite different LED currents and voltages. These were actually observed and shown in another video. Select a few positions of the potentiometer, measure the frequencies and compare with this calculation results. This frequency is nearly 3 times the previous, due to the change of the potentiometer knob. A demonstration used a low capacitance, 10 microfarad, to observe higher frequency, for which, the eye cannot tell, and it was measured with a photodetector.